last time for the expression for the effective tangent minus 851 L effective Just make sure this is what you are going to do. Log lambda. These are the divergent parts. Then I have minus 1/8 omega 4 log omega square by 2. And the last term I am ignoring, which is the one involving that gamma times omega to the power 4, because that is ignorable compared to this one. So before we do anything further, let me just write down the corresponding effective potential, which is essentially the same thing, because the L effective, we are doing Euclidean, so L effective is same as V effective. Okay. So the V effective, which comes from this, there is of course the original potential Vf5, which I am not writing. So this V effective is the correction to that original potential. That will be 1 over 32 pi square V double prime by lambda. I have used the fact that omega square is equal to V double prime plus half V double prime square log lambda. This is from this term. These are the two divergent terms. Then I have a finite term, which is 1 upon 64 pi square V double prime square log V double prime by 2. So this is what we want to set. Fine. So let us look at the structure of this. You started with a given potential V of phi. Then we said that this phi can be separated into a slow modes and fast modes. And the slow mode is what we have called capital phi, and all these things are functions of that capital phi. Then the fast modes are the linear departure from that capital phi, and we integrated out that fast modes in the quadratic approximation. When we do that, we find that your original potential picks up a correction which is of this type. Okay? Now, we also found that when we did this calculation, there is an integral which needed to be cut off, and the cutoff scale we introduced was lambda, and lambda was a cutoff scale in the length, more precisely in the square, because if you remember, we had an integral from the form integral over ds with e to the minus something like s p square kind of structure. So S has dimensions of this inverse p square, which is length square. So lambda has dimensions of length square. Let me write that down. So this lambda has dimensions of length square, which is same as the dimensions of energy to the minus 2. So I could sort of put some E infinity minus 2 for lambda. Okay. E infinity is to remind you that at some level we are expecting that scale to be sent to infinity. Okay, so this is what we have. Then, if you look at the structure of this, I also pointed out that this is a little disturbing. You don't want to have a logarithm of a quantity with dimensions. So in principle, I could have divided this by some parameter, and I could have put the same parameter here, because you notice that 2 is 32, this is same term as this, 64 pi square, v double prime square and a v double prime square. There are the logarithms which will add up. We did it like this because we wanted to separate the divergent quantity from the finite quantity. Otherwise, I could have just put this v double prime along with it. Okay. So what we will do is to put some lambda divided by some constant. Let me call that constant mu, and then I can put here the same constant. So nothing has changed, and now the dimensions are taken. So if lambda has dimensions of 1 over energy scale, so this term is actually log mu inverse divided by, so I am just putting it on top, E infinity square. So again, mu inverse is some energy square, right? So let me call this some log, some m square upon A infinity. What it means is that this entire operation has introduced another energy scale m square into this. From the way these logarithms appear, it looks intuitively sort of better to think of this as arising because we have integrated out modes between, let us say, m and E infinity. So I explained to you the other day that the entire philosophy of renormalization group is that you take the energy scale, put a cutoff scale which is E infinity, and then you take a scale m and you integrate out all the fast modes which have energies between m and E infinity. These are the high energy modes. And you look at the physics at scales which are far below this here. Okay, this is what we are doing. And that m will also appear here in this video. So far everything has been purely formal, and we haven't even said what to do with this divergent term. Okay. Now comes the crux of the matter. Suppose your original v was some polynomial, just to give an example, because we are interested in things like lambda phi 4 in the end. So you think of this v of phi, the original v of phi, as let us say something like summation Cn phi to the power n. Okay, with n is equal to, let us say, some 1 to some capital N. So it is phi plus phi square plus phi cube plus phi to the 6 or whatever, right? Presumably we should only keep even things, so it doesn't matter, it's purely a formal argument. Then you look at the degree. So this is a polynomial. So this term is going to be a polynomial and this term is going to be a polynomial. Because we are only interested in the divergent terms for the moment, this will give you something. Okay. So if you look at the divergent term, v double prime will be a polynomial of degree n minus 2. That is okay, because if you produce a polynomial of degree n minus 2, so this is going to be an expression in which there is an n minus 2 degree polynomial in phi, but you take this constant Cn and all these divergent terms can be reabsorbed into that. So that is not an issue. The dangerous thing is this object. Now if you take v double prime will go as a polynomial. It will be a polynomial of degree. If it is n, it will be of degree n minus 2. Right? Therefore, because I have taken two derivatives, so this is up to n, so it is n minus 2. The highest term will be of n minus 2. Therefore, v double prime square will be a polynomial of degree 2 into n minus 2. So when I look at this term, I will generate a polynomial with all the terms up to 2 into n minus 2. But in the original theory, I had only up to n. Alright. So as long as my 2 into n minus 2 is less than or equal to my original n, I am fine. Because I have n constants to tinker with. And if the new the calculation here does not generate any new powers. The powers generated are the powers which are already present in my effective potential. Then I can reabsorb all the divergent terms into those constants. So this is a very nice result because it tells you 2n minus 4 has to be less than n, or n should be less than or equal to. This gives you the significant result, at least in this point of view, that lambda phi 4 theory should be perturbatively renormalized. But if you go beyond that, this will break. So this n is equal to 4 comes from there. And you, as you can see, it is a dimension dependent statement, but we are thinking of 4 dimensions right now. So what happens here is the following, just to give a concrete example. So if you start with a theory which is like V of phi is say half m square phi square, we will do in detail in a minute with lambda by 4 factorial phi 4. Then your V double prime will go as one term, okay, m square phi. This will give you, when I take 2 derivatives, it will have only m square, and this will give me lambda by 2 phi square. So the V double prime square term, which is the dangerous term, will be a square of this. So you see that it will have some constant which I don't care. Then you will have a term with phi square and you will have a term with phi to the power 4. Right? So I will have a term with phi square multiplied by a log lambda by mu. The term with phi to the power 4 multiplied by a log lambda by mu. And of course that V prime which is written here, which was this, will also get multiplied by some lambda. So I just take all these quantities and I add it to the original terms which are present in m square and lambda. So if I have thought of this as some original values, m naught and lambda naught, when you add them up, I end up getting the same kind of a structure with m naught and lambda naught replaced by some new set of variables, new coupling constants and new mass parameter, plus a non-trivial finite term. So this is in a gist what the renormalization of the coupling constant does for you. So you start with a theory and you integrate out certain degrees of freedom and it generates new terms in the effective potential. Some of them could be divergent or cutoff dependent. That is a more precise statement, cutoff dependent. And the cutoff dependent terms are reabsorbed into the original coupling constants of the theory. Once you have done that, you have got a theory with a new set of parameters, m and lambda, plus a finite term. The only non-trivial thing is, the finite term will now depend on a parameter mu, which you don't know what it is. Okay. However, the full potential actually does not depend on that mu, because by construction I know this potential V effective does not depend on mu. I have put in a mu here and I have put in a mu here, so it cannot. What it means is that the lambda which we get from lambda naught and m which we get from m naught is going to now depend on mu, or on this scale m, capital M, which I am talking about. And if I change the scale m, this is called either a renormalization scale or a integration. Yeah, 1 second. Terms here, the new coupling constants are going to now pick up this m dependence, which is precisely what we mean by saying that it's a running coupling constant. If I now take the coupling constant that ostensibly depends on this m, but from a practical point of view, the parameters which appear in the Lagrangian can only be given meaning after you do some experiment and determine its value. I mean, this is what I meant about the effective mass of the electron. If you are having a crystal lattice and you can take the electron out, then you can measure. But you can never switch off the interactions of the field with itself, which is always there. Therefore, what you do is the following. You do some scattering of these mesons on itself. In fact, when we do it in the perturbation theory approach next week, it will become a little bit more clear. When you do the scattering cross section or the propagator or whatever which you measure from the scattering cross section, you will have the value of lambda related to some physical process which is taking place at some energy scale. So suppose you scatter the particles at some energy scale E, then you fix the value of lambda at that energy scale. This some experimentalist has to give. Usually you give it at very low energies or whatever, but you give the value of lambda at some scale. Then suppose I do the same experiment at a different energy scale. Okay, I will know what coupling constant is. That is given by how this coupling constant is going to depend on that E. And what we will find is that that result is independent of E. That is the crucial point. This E infinity hangs around all over the place, but when you finally write everything down in terms of observable quantities, the E infinity just goes away. As a result of which, the cutoff which we have put in and then sending to infinity, in between stages, if you try to send it to infinity, there are things which diverge. But finally, when you look at everything in terms of observable quantities, it doesn't appear. Okay, at least in a wide class of cases. So this is the entire philosophy of renormalization too. That if you talk in terms of observable quantities, observable parameters in the Lagrangian, measured by some particular experiment at some energy scale, then if you know how these coupling constants run with the energy scale, then you can predict results for any other energy scale. Fine. Now one more comment. This entire analysis is essentially dimensional analysis, and here is one case where things actually, the power of dimensional analysis really comes true. When you do something like this, suppose I started with phi 4, then I got this. Just as an example, suppose I look at V of phi, which is some 5 to the 6. Okay? The way I will write this is that I will put some lambda 5 to the 6 divided by, let us see, some V square. The idea is that the potential which I have is going to be integrated over d4x in the Lagrangian, and in the natural units which we are using, potential times d4x should be dimensionless, right? Therefore, the potential should have the dimensions of mass to the power 4, mass and length as inverse dimension. So, potential should have the dimension of mass to the power 4 or energy to the power 4. So, phi to the power 4, the phi has exactly that dimension, so lambda was dimensionless. Phi to the power 4 d4x is dimensionless, therefore lambda in our lambda phi 4 theory is dimensionless. So here if I put phi to the power 6, it is good to compensate for it by introducing an energy scale V. Okay, so that this has again the dimensions of phi to the power 4 and this lambda is dimension. So it's just a way of writing. Of course, lambda by V square is the coupling constant. But you can keep lambda as dimensionless and introduce an energy scale. Now suppose if you calculate V double prime, you are going to have a term which goes as lambda phi to the power 4 by V square. So the square of that is going to give me phi to the 8 by V4 lambda square. So you started with phi to the 6, but now you have generated a phi to the 8. This is a losing proposition, because we can say, okay, suppose I add a phi to the power 8 here. But we know that by the analysis which I have done there, phi to the 8 will create a phi to the 6 square, which is phi to the 12. So this will keep going up. Okay. Therefore, you cannot add terms and make that theory good. And again, in the old-fashioned way, one would have said that these theories are bad. Don't study such theories which has interactions like phi to the power 6. A slightly more, let us say, benign approach to such theories would be to say that yes, it is going to generate this correction, but when you look at it, you know that it has the v to the power 4 term sitting in the denominator. So the corrections which you are going to generate are going to be suppressed by this energy scale. And higher order corrections will have higher and higher powers of this energy scale. Therefore, I mean, phi will go away when you calculate scattering cross sections and all that. But the coupling constant will remain, which means that lambda square by v to the power 4 will remain. And when you finally want to have something which is dimensionless, this will get multiplied by an energy to the power 4. That is, the physical processes will go as lambda square into e to the power 4 upon v to the power 4, where e is the energy scale at which you are studying the physical process. Now there are two possible ways of looking at it. The old-fashioned view is to say that, look, there is a e to the power 4, which when you go to very large e, it is going to kill you. The another point of view is to say that, yes, but this theory is valid only for energy scales much below v. So you look at it, and if you just want to calculate the corrections to whatever you had originally predicted, because of this extra quantum effects, they can be computed for scales which are far less than that scale which appears in the problem by this sum. Actually, a classic example of this is indeed gravity. The difference between theories like this and theories like this and theories like this is essentially that in this theory, the coupling constant is dimensionless, which means there is no other energy scale in the problem. In a way, that is why logarithms come up, because there is no natural energy scale in the problem. I mean, let us not worry about the mass part, because mass part comes in the free part of the theory. Okay, we can handle the mass part. So in the interaction part, there is no energy scale. But if you look at this, the interaction part of the theory has an energy scale. And that is why when you calculate scattering cross sections, etc., that e to the 4 upon v to the power 4 terms will. If you look at gravity, gravity has something called Planck line. I mean, what you call G, the Newtonian gravitational constant, will become G h cross upon c cube when h cross and c are 1, which is Lp square, which is a length scale. And from that length scale, you can construct an energy scale, which is the Planck energy. So you will find that just like this v square, there are Planck energy corrections which will appear if you attempt to do the same sort of thing with gravitational Lagrangian. So again, the standard point of view is that this makes gravity non-renormalizable. So you can, by which we mean that highest energy processes where energies are comparable to the Planck scale, we have no way of controlling them or computing them. But gravity is still a very good low energy effective theory, and you can even compute quantum corrections to processes with energies far less than Planck energy by using that effective field theory. Okay? So this is what we want. Okay. Now let us go and complete this program. Let us say that we are looking at this kind of a structure. There is a m naught and lambda naught, and you add these coupling constant, add these divergent terms to this, and you look at the renormalized lambda and m, which essentially involves taking this, plugging it into this, and computing each of these and adding them up. Okay? So this is a straightforward computation. So let me just give you the result. It is there in the handouts, and you can work them out. When you do this, you find that the final result can be written in the following form. The total V will turn out to be half m square phi square. Originally you start with the m naught and lambda naught. Now it becomes m with no subscript. M square phi square plus lambda. Okay, I had not used 4 factorial, but I used 4 in this note. 4, 5, 4 plus V finite, which I will write down, which is essentially 1 upon 64 pi square, that last term there, times m square plus lambda by 2 pi square, a whole square, log 1 over 2 mu, which is that parameter we introduced, the same quantity, m square plus lambda by 2 pi square. Okay? This is the finite part where your m and lambda are given by M square is given by M naught square plus lambda naught upon 32 pi square one over lambda and N naught square log lambda and lambda, which is more important for us, is given by lambda naught plus 3 lambda naught square upon 32 pi square log lambda. Okay. So now let us look at what this means. So we have completed the process. Just to tell you what we have done, we take this expression for V effective, add to it this original term, and use this to compute this V double prime by lambda, V double prime square times this log lambda by mu. And when you do that, you are going to end up terms which involve this, right? Then you combine the terms which is of different order. You throw away constant terms which you don't care. There will be a term which will be lambda by 2 m square phi square, or lambda m square phi square with a factor 2 taken away. So this term is going to sit here with a log of lambda by 2. Okay? That will add to your original m naught square. That is how you get this term. Similarly, when you look at the phi to the power 4 term, there will be something which will come from lambda square by 2 here. Okay, these things should be m naught. And lambda naught square by 4 times that phi to the power 4, and that term is going to be multiplied by this log, and that is what comes here. So you have reabsorbed those terms, and this is the most important part of this procedure, so make sure you understand that. What you have done is that you started with this, and then you obtained a corrected potential. In that corrected potential, your m naught and lambda naught get replaced by m and lambda, which is related to your original m naught and lambda naught by this relation. What remains here is a finite quantity. Okay? Now, the only point is the finite quantity seems to depend on some mu, but we know it really doesn't, because these things also depend on mu, and they depend on mu in exactly the same way in order to compensate for it. This we could do only because the theory satisfied this condition, and the new terms which were generated could all be reabsorbed into the old terms. Now let us stare at this coupling constant a little bit more, and that is essentially all that we need to do in this particular example. So let us look at that quantity. So I said that lambda, okay, so let me write it down one second. Lambda equals lambda naught plus 3 lambda naught square upon 32 pi square log lambda. I should also make one more comment here. The point is that when you write these things down and you look at this finite quantity, it actually is m naught and lambda naught. But we are assuming that this is some kind of a correction to this, to the lowest order. And in the lowest order, we are replacing that m naught and lambda naught by m and lambda. So in that sense, you should think of this as a perturbation in the coupling constant. You originally had a lambda naught term, you have generated a lambda naught square term. There could be a lambda naught cube, etc., etc. But remember that even though we are doing an effective potential without doing manifestedly a perturbation series in lambda, we did truncate it as quadratic. because in order to evaluate the path integral, we have to truncate at quadratic order. So this is not exact, there are corrections to that, so that should be kept in mind. So that is the way, that is the interpretation which has gone into this. Now let us bring this in terms of energy scale. Lambda naught we said as a S times p square, so S is like lambda, and we said that it is a E infinity to the minus 2, right? So I wiped it out. What I said was, this is important, the dimension of S is same as the dimension of lambda, and the dimension of that is 1 upon energy square. Okay? S was like length square. So you have this. So let me write it in terms of some energy scale square upon E infinity square. Right? I hope you got this argument, because here we keep switching back and forth between energy scales and length scales. When you are doing the integral in that LFFQ to compute this, we did an integral over S, which came in as e to the minus SP square. So S had the dimensions of 1 upon P square or 1 upon energy square, while the lambda which we put was a cutoff on S, therefore this is like an length scale cutoff. While normally in high energy physics one would like to think in terms of energy scale cutoff. So these are, I put it down right here and I put a lambda. Now you ask, what is the difference between lambda at some m minus lambda at some scale m prime? This is crucial because this m is what is going to go and sit here. See this mu, I just replace mu by m square. So I can put an m square here. Right? So this is crucial, and this seems to sit in the finite part of the effective potential. So I want to know what m I should use, or rather if I change my m, how the coupling constant changes. So that is given by this relation. From this we immediately find that this is equal to 3 lambda naught square upon 32 pi square. Okay, let me take it as lambda at m prime minus lambda at m. 3 lambda naught square upon 32 pi square log m prime square minus m square. I am just subtracting these two. So think of m prime as slightly different from m. From m I am moving a little away. So this to the lowest order, this can be evaluated at lambda square at m itself. Okay. If for a moment I write this as 3 lambda square upon 32 pi square log m prime square minus log m square, then I can combine all the terms with m prime and all the terms with m together, and what I get is that lambda of m plus 3 lambda square upon 32 pi square log m, rather log m square, is a constant. Let me just make sure the coefficients are correct. Yeah, there seems to be a sign issue. Let me just make sure. Yeah, there is a sign issue. So when I move lambda m to that side, that comes with an opposite sign. This is good. Okay. So what does these result mean? What it tells you is that If I had originally evaluated the coupling constant at some length scale m, suppose an experimentalist friend has done a scattering experiment at some energy scale m and has told me that lambda at some 3 GeV is equal to 0.1. Now I want to study a scattering experiment at not 3 GeV but at some 30 GeV. Then I want to know what coupling constant I should use. Here is an explicit formula which tells you how to do it. This is very nice because this formula is completely independent of the cutoff scale E. Once you have come up to this level, you can now send E infinity to actual infinity, and that divergence is completely disappeared.
So this is the running.
This is the running coupling constant. Okay. So what you say is that this coupling constant sort of runs with the scale, and at every scale it has some particular value. The running on the coupling constant is sort of more formally designated. You take that 2 out, so designated by taking the following quantity. You take m d lambda by d. Almost invariably you will have this logarithm, so that is why you are essentially calculating the variation of lambda with respect to log m. And in this particular case, it is going to be 3 lambda square upon 16 pi square. This quantity goes in high energy physics, we name the beta function of the theory. So this is beta of lambda. So once you know the beta function of the theory, you know how the coupling constant changes with energy. Here, for example, you find that the coupling constant sort of increases with the energy scale, right? At higher and higher energies, it is more strongly coupled, and at lower and lower energies, it is going to be weakly coupled. Now, this has lots of importance for the formal structure of the theory. Now, if you think of this theory as some very exact kind of a description of nature in some sector, then suppose it had a coupling constant at very high energies. Suppose you start with that, and then you keep decreasing the energy scale. Then what it tells you is that the lambda keeps decreasing, and at very low energies, lambda just goes to 0. Rather, it just dies down. So this coupling constants, it becomes very weakly coupled theory at low energies and becomes strongly coupled at very large energies. On the other hand, you can have a kind of a situation like in QCD, where you have quarks. Now the quarks behave as though these are like little balls tied by a string. Suppose you have 2 balls which are tied by a string, and the balls are moving around. If they are moving around at a length scale which is smaller than the total length of the string, then it doesn't feel any force. It can just freely loiter around. But the moment you try to move the balls at a distance which is greater than the string sort of gets it together. This is why the quarks, which when you see in deep inelastic scattering inside the baryons, protons or neutrons, they appear to be like free particles. Okay, they are not bound to anything. But at the same time, no one has ever succeeded in getting a quark out of as a free quark. So the quarks are, so to speak, the quarks are confined, and there is a confinement phase of this QCD which describes the baryon. This implies that the quarks do not have some asymptotic free state. You can't say that when the quarks are infinitely separated out, they don't interact or something. So this is a situation at very low energies, the coupling constants are very strong, as a result of which it gets coupled. Low energies meaning at large scales. At large scale, the coupling is very strong, but at very small length scales, the coupling is weak, and it looks like a strings and a ball kind of it. That would be reflected in the beta function of that. And in fact, one of the recent Nobel Prizes were for the work which did and computed the beta function in QCD for the first time. And until that time, people did not quite realize the importance of this, and this was one of the first times this calculation was correctly performed. And one realized that the confinement of the quarks has something to do with this. So this is fairly non-trivial, both theoretically and observationally, because you can actually do things with it. And this relation finally tells you that all the formal manipulations we did with the infinity, etc., in spite of all the divergences, you can make statements which can be checked against experiment, because you get a concrete result which tells you how the coupling constant is running with the scale. Okay? Now, if you have been again switching back to the condensed matter paradigm, then it is a lot easier. I told you yesterday that if you think of spins on a lattice, and you take a block of spins and you take another block of spins, and you see what they are, how they are coupled. Obviously, the coupling between these two things will depend on how many spins or what size lattice you are looking at. So when you average over certain regions, you are coarse graining over length scales, which is like saying that you are integrating out high energy modes. So as you keep integrating out high energy modes, your coupling constant changes. That is another way of interpreting this system. You say that if I keep one of the things fixed, let us say I keep m fixed, and you think of m prime as some b times n. B is just a parameter. So this will just give you a log b square or log b once I take the 2 out. So there is a log b dependence there. So if I double the b, that is you look at a scale m, then you look at the scale m by 2, then you look at a scale m by 4, etc. Every time I double that, I am going to pick up this much of change in the coupling constant. Okay, this is exactly what would happen if you have a lattice and you keep doubling the lattice size, and that paradigm just fits. Okay, so this is all that I want to do with lambda flexible theory. Later on, we will take this up in a federative approach next week, where we will try to connect up exactly how this lambda can be related to some observable quantity and how the same result is applied. So with all the 3 lambda square and 32 pi square and what. Okay. Now let me move on to another example, which is in some sense nicer. We want to study the interaction between complex scalar field and electromagnetic. So what we want to do now is to look at the another Lagrangian which we have studied before, which is d phi, which I gave you as an example yesterday, d phi star d phi minus m square phi square minus 1 for Prof. Okay. So here we are not looking at the same field and dividing that into slow and fast modes, but we are thinking of a scalar field which is coupled to an electromagnetic. So what we are going to do is the full formal theory will be an integral over the vector potential AI or A, and an integral over phi and phi star, there is just known as phi, of this action, which is e to the I times integral d4x of this Lagrange. So we want to do the integral over phi first. So this will turn out to be integral over d aj. You will certainly have here e to the I integral over d4x, this piece of the Lagrangian, because that is independent of phi. Then you will do an integral over d phi and phi star of e to the I, the Lagrangian for phi, d4x, let me just write it as L of phi. So this L of phi is these two terms. And this is the L for the electromagnetic. Okay, this is what we want to compute. So let us just make sure you get the orientation back from the self-interacting lambda phi 4 to something else. So here you have honest to God two fields which are interacting with each other, and I am going to integrate out one of the fields, which is the scalar field, complex scalar field, and I am going to ask what is its effect on the electromagnetic. Okay. So when I do that, in some sense, this F or the electromagnetic field is sitting inside this. There it is sitting inside it through this D, because the D has a partial I minus Q times AI. So the electromagnetic field is sitting there. So you are studying a complex scalar field in a given electromagnetic path. As far as this path integral is concerned, the electromagnetic field goes for a run. This last path integral is concerned, d phi path integral. So you have a given electromagnetic field and you are integrating out the phi in that. After you do that, your answer will just depend on the electromagnetic potential, right? So this is what we would have thought is an effective action. So you will end up getting this as some dAj e to the I integral d4x of minus 1/4 f square plus some L effect. This e to the I integral d4x L effective is coming from this. Now what do you expect? This electromagnetic field in some sense is like our JFX. Originally when we did the scalar field, we had the scalar field coupled to an external source JFX and a JFX pi of x was there. So it is, this electromagnetic field is like a JFX and we are quantizing the scalar field in the background of that JFX or in the presence of that JFX. When you do that, you will get this. This is nothing but the in-out or the 0 plus 0 minus vacuum to vacuum transition amplitude in the presence of the electromagnetic. Now you expect two things. First is that the electromagnetic field will induce some changes in the energy of once you integrate out the complex field, whatever remains, the L effective will have a real and imaginary part. The imaginary part can be thought of as the external source, in this case the electromagnetic field producing particles. So if I have an external electromagnetic field and if I do end up getting an imaginary part, which we will, it shows that this external electromagnetic field can produce the scalar and the scalar particles, the charged particles out of vacuum. That is the first phenomenon. The second phenomenon is that when this happens, the energy of the vacuum state is going to be changed. Originally the energy of the vacuum state was half h cross omega for the scalar field. Now you are switching on an electromagnetic field, which means the energy, the ground state energy is going to pick up a contribution depending on the electromagnetic field. So the energy of the electromagnetic field will change, which is equivalent to saying that the effective Hamiltonian or the effective Lagrangian for the theory has changed. That will be contained in the real part of the L effective. So the real part of the L effective will correct the Maxwell's equation, because remember that minus 1/4 f square, if you vary, you are going to get Maxwell's equations. Now you are going to get a correction to the Maxwell's equation. Okay? And there is also this phenomenon of particle production. So we want to compute L effective and look at its real part and imaginary part. This is what we are going to do. Okay. Now the computation turns out to be a little bit messy. So I am going to use a series of tricks to simplify it, and I will try to show you how to do that. The first point to note is that since we have very carefully constructed a theory which is gauge invariant, if I use a measure which is all perfectly correct, then I should get an L effective which is gauge invariant. That means whatever it is, it can only depend on things which are gauge invariant and which are Lorentz invariant. Of course, it should also be Lorentz invariant. This tells you that since this f square is essentially built out of electric and magnetic field, this L effective can only depend on two quantities, E square minus B square and E dot B. These are the only two gauge invariant, Lorentz invariant combination you can get from f square. Okay? But it can be powers of that, etc., etc. So for convenience, we will introduce two more quantities, which you call A and B. By the definition, A square minus B square is equal to E square minus B square. And AB, A and B are just numbers, is E dot B. So A and B are gauge invariant, Lorentz invariant numbers. Of course, you can solve for A and B from this. If you know A square minus B square and AB, you take a 2AB and add and subtract, you know A plus B and A minus B, and can solve for A and B in terms of this. You will get a messy expression, but you don't need that. You will never need that. So this is the expression you have. Then you say that because it is Lorentz invariant, I can perform this entire calculation in any Lorentz prime I like. Okay? And we are interested in a generic case of electric and magnetic fields. Therefore, I could have chosen an electromagnetic configuration at a given point where E and B are parallel to each other. Except when E square minus B square is 0 and E dot B is 0, which we won't consider. We are looking at a generic electric field where that condition is not satisfied. You can always make a Lorentz transformation such that E is parallel to B. You should convince yourself of this if you don't know this result. This is a standard result. You boost in a direction along E cross B, because E cross B is the direction of the momentum flux of the electromagnetic field. If you move in that direction, there will be no momentum flux. You can neutralize it and you can have E and B parallel to each other. So if E and B are parallel to each other, something nice happens. You can immediately solve this by inspection. A is equal to E and B is equal to B. Okay? So what we will do is that we will work in a frame in which we will compute L effective as a function of E and B. E and B are in the same direction, so only their magnitudes matter. This is the magnitudes of E and B. Then once we have got a final result, we will quietly replace E by A and B by B. Once you have done that, you have an expression entirely in terms of A and B, and that will be valid in an arbitrary Lorentz prime and in an arbitrary gauge. Right? So that happens just because of the argument which I have presented. So we are making maximal use of gauge invariance and Lorentz invariance. Okay. Now we want to do one more thing. Just as we were when we were studying the lambda phi 4 theory, we divided things into slow modes and fast modes. Here also we are going to study the quantum fluctuations of this phi on a background AI which is varying slowly. More precisely, saying AI very slowly doesn't mean anything because AI is not a gauge invariant concept. You have to say that Fik is approximately constant. So the electric and magnetic fields are treated as approximately constant. So the vector potentials will be linear. In this. Okay? So that is the approximation in which we will be working. Okay. So given this much, what we have to again evaluate is our old friend, the expression for the L effective. So the L effective is now given by minus I by 2. This one I am starting to do in Lorentz gauge. We will then pick to Euclidean sooner or later. So it is 0 to infinity ds over s x e to the minus is some operator, let me call this some character h x. Okay, this operator is essentially what is sitting here once I have done an integration by part. So we know the expression for that, we have done it before. So this h is with proper signs, it is minus I del minus QA the whole square minus epsilon. Now, previously we used to write with this I put on this, which means that if I take this I out, I'll get a square of that which is a minus sign, that will cancel with this, and this will become plus, and this will become d plus iq, but that is the same thing. So if you work this out in this notation, it turns out to be slightly easier. That is why I have written it like that, because I del can be identified with momentum, okay? So it is more convenient to work with this. So what we have to do is to compute this quantity where h is given by this. And you need to know what A is. Of course, the way I have written it down, it is a bit formal because there is a DI here and a AI here because it's a vector potential, and the square means that you are taking the dot product of that with respect to itself. Okay. So that is what we want to do. So in order to do that, we want to choose a frame in which you can write down the explicit form for the electric, the explicit form for AI. We will take AI to be minus EY zero minus Px. Okay. If you do it like this, you can easily show yourself that both E and B are in y direction. That is, E will be 0, E 0, and B will be 0, B. Notice that the first component is the scalar potential. So the negative gradient with respect to y is going to give you the electric field in the y direction. Then here is only a z component. So the curl of that with respect to the derivative of z component with respect to x with the proper sign will give you the magnetic field here. So curl of E is B and minus gradient of phi is equal to E, and this is the gauge which will be working. So what we need to do is to plug this into that and simplify the expression for this one. Okay? And then we have to put this into this and compute it. So let us see what that H is going to turn out. So the H will be equal to, let us see, minus, first we start with I d by dt, that I will call it as dt, minus Q times the key component of this, which is EY, so that is Q EY, the whole square. Then let us look at the x component of that. So when I take x here, I need AX, but AX is 0, so that is easy. So it is just minus d square by dx square. Then I look at y, and y also I have this y here, but ay is 0, so that is going to be minus dy square. Then I come to the z, so then I will have plus I dz, and this is what contributes there, plus q bx, the whole square, and minus m square. So this is the operator we need to work with in order to compute this quantity. Okay, so let me just make sure the signs are correct. Yeah, the signs are correct. So this is, there is an overall minus sign. Yeah, there is an overall minus sign, and these two things pick up this I, and therefore there is a negative sign. Okay, fine. If I am going to plug it into this, and I want to compute this kernel, let us go back to what I said yesterday. Anytime a particular coordinate here, these x's again are xi, so it is t, x, y, z. Anytime a particular coordinate is not there in that H, it is easy because I can just replace it by the momentum. That is, the derivative with respect to that coordinate can be replaced by the momentum, and I can just remove the integration out of it, integrating over the relevant momentum. Okay? So what we really need to work out are only those derivatives which has the coordinate dependence sitting here. So there is a y and an x, which I cannot do anything about, but I am okay with t and z because nothing depends on t and z. So I will write this by replacing those quantities. This object here, this x e to the minus is h x will therefore become, by this argument, you will have an integral over dp0 corresponding to the time and a dpz corresponding to the z coordinate, both of which are absent in the calculator, in the operator, times a reduced quantity which depends on only x and y. So let me call this transverse directions. Some other operator, let me call this capital H, transverse direction, where I have to write down what that H is. Let me try to write it here. So that H is obtained from the curly H by replacing these by the momentum terms. So that will be minus P naught plus QEY the whole square plus dy square plus dx square minus dz plus qbx the whole square plus m square. Okay, let's make sure the signs are all right. So this minus, when I take it inside, is going to give you a minus sign on this, which I have taken into account. Then these two signs go away, and then this is going to give me a minus sign, and this is going to give me a plus sign. Okay? What does this mean? And also this d by dt I have replaced by minus p naught, and d by dz I have replaced by pz, which is our standard convention that time and space should have a flip in the sign. So what does this mean? What it tells you is that this is, let me just describe this and then we can take up the computation tomorrow. What it tells you is that ultimately what I want to compute here, this LF active, is going to be an integral over ds over s of some object here, and that quantity in turn is evaluated by substituting for this h wherever it is there is an ignorable coordinate, the derivatives by the momentum. So I want you to make sure you understand that first, because yesterday when we had a e to the minus s box, we replaced that box by minus p square. That we did because you can go into a momentum basis, introduce a complete set of momentum basis. Normally it would have given you an e to the minus ip x minus x prime, but remember that we are doing a coincidence limit, so that is not going to be there. And all that we will be left with is an integration over dp naught and dpz, okay, upon 2 pi square. So in this h I can get a reduced Hamiltonian where these terms are replaced by the terms involving the momenta, which is what I have done, pz and p naught. They are going to be integrated out here finally after we have computed this material. So what we are now left with is that there is a xy space, ordinary xy space, and in that plane I have a e to the minus ish. So this is reduced to a two-dimensional quantum mechanical problem. So think of a two-dimensional quantum mechanical system where the particle states are labeled by xy and x prime y prime if you feel like, and there is a kernel, path integral kernel, which I am going to compute. This is exactly the propagator for a particle to go from this point to this point. It just turns out that these 2 points are the same, so in the end of the propagation we can take the coincidence limit of these two, or a Hamiltonian which describes that particle. Now what is that Hamiltonian is what we want to look at. Now in order to look at that, you find that there is a y plus this junk. So suppose I take this QE out of this. So let me write it here. Let me write this out here. So let us look at that form for that head. I'm going to take inside it, there is a minus, and take that QE out. So it is minus Q square E square and y minus P naught upon QE, the whole square. Okay. Then I have a plus dy square. Then I have another term which is plus dx square minus, there is a q square b square into x plus px upon q. Then you have an m square. There is a sign thing.
BJ.
Yeah. Then you have a h which has an m square. That I don't care, because that m square will just go for a ride, e to the minus s m square, and it is just a constant addition to the Hamiltonian. But so let us look at this Hamiltonian. But if you want to, we can just keep it there. Okay. And again, I am not always sure about the signs, but that we can sort out when you have the handout or whatever. The crucial point is there is a dy square and a dx square, which are like the momentum terms. It is like del square. So it is like the momentum terms for the x and y coordinate. And if I shift x and y coordinate by this amount, that is instead of y minus this, suppose I call this some y bar or whatever. So I get a y bar square here, and I get here an x bar square, right? But this sign and this sign, okay, there is some problem there. Okay, I have made a mistake in one sign somewhere. We will come back to that. One of them will be plus and one of them will be minus. Okay, so let me put it this way, and I will sort it out in the next lecture. So this sign and this sign is opposite. What will happen is that this is clearly a quadratic in the coordinates. So you are going to have a harmonic oscillator in the y direction and a harmonic oscillator in the x direction. One of them will have the correct signs, and I happen to know that the magnetic field will come with the correct signs. Okay, so this should be minus here because this should have overall minus sign, and this should be plus. So there must be some error in running it through. So what you will find is that the x looks like a harmonic oscillator variable in one dimension with a frequency which is decided by QE, and the y looks like a inverted harmonic oscillator with a frequency QE. As far as this Hamiltonian is concerned, it is completely solved because it has been reduced to two separate quantities. One which involves, this is exactly what you would have had if you have a harmonic oscillator in the x direction and a harmonic oscillator in the y direction, with the difference that one of the harmonic oscillators has a direction which is, has a sign which is the sign for omega square, which is opposite of the conventional, right? But it is still a quadratic potential. Half m x dot square minus half omega square x square or plus omega square x square are quadratic potentials. So by changing omega to I times omega, I can evaluate the path integral for either or not. So I know the path integral kernel for this problem. So the path integral kernel for this Hamiltonian can be written down. The coincidence limit of the path integral kernel. That's how the entire problem can be solved. Okay. So this is the whole analysis. So I want you to get the logic of that because this is probably the most involved computation we are ever going to do in this entire course. Okay. Everything else is fairly trivial. If you start with this Hamiltonian, you choose your gauge, and then you plug that in, then you will get a Hamiltonian which is of this form. Okay. what you do next is that when you compute this, you notice that the T and the Z does not appear in the potentials of the Hamiltonian because only X and Y appear. Therefore, the T and the Z can be replaced by their momenta, which you do by d by dt you replace by some minus P naught, and d by dz you replace by P. Once you have done that, you have reduced the problem to a two-dimensional problem. And that two-dimensional problem happens to be two separate one-dimensional problems. In one direction, it is a harmonic oscillator with a honest-to-God frequency. In the other direction, it is a harmonic oscillator with an inverted frequency. Okay. The honest-to-God frequency, I just happen to know, because I am sure if you work this out, it will turn out to be correct, because this one and this one will have the opposite signs. So, the harmonic oscillator with the correct frequency is the one which corresponds to magnetic field, and the harmonic oscillator with an inverted frequency is what corresponds to the electric field. Except for that, everything is the same, and the frequencies are just QB and QE. Then you can write down the path integral kernel for this and take the coincidence limit. That will give you an expression, and once you have that expression, you integrate this over ds over s, and that will give you the electric. Okay, so this is going to be the strategy. Now you can also roughly see, and that is why I was emphasizing that, the inverted oscillators are in some sense unstable. Right? If I have an inverted oscillator and I sort of put a particle somewhere, the particle will run away to infinity, so to speak. It has no lower bound in the Hamiltonian. While the normal oscillators are stable. This translates in this theory into a constant electric field, making the vacuum unstable and producing pairs of particles, while a constant magnetic field will not do that. Eventually, when you work everything out, you will find that it is the electric field which leads to an imaginary path to the L effective. And if you had only a pure magnetic field, it will not have an imaginary. So the magnetic fields do not produce particles, while the electric field do. A very rough way of thinking about this is that if you think of a quantum vacuum which is filled with these virtual particle-antiparticle pairs, and if you put an electric field in it, the electric field can do work on the particle. As a result of which, it can sort of give it enough energy which is more than this mc square and convert the virtual particles into real particles. The magnetic fields do not do work on the particle, so it cannot produce the particle-antiparticle pairs from the vacuum. This is not a very strong argument, but that is an intuitive way of thinking about it. Okay. So this computation we will complete in the next class. Questions?
In the electric fields, they can give rise to the virtual particles.
Yes.
So in terms of the off-shell process and on-shell process, how can we understand that?
Where does off-shell or on-shell?
Off-shell, I mean, in case of virtual particle, is off-shell process
related okay. So the way to think about this is that you take a particle-antiparticle pair, and let us put an electric field on that region, and then you ask in a small time scale delta t how much energy this electric field can give to this particle, okay, or how much it can be separated out or whatever. If you find that the time scales or the energy scales which are involved are all scaled as some based on energy is mc square, and that will give you a time scale, etc. And you can say if the force acting on a sufficiently small time scale can give you an energy which is greater than 2 mc square, the virtual particle becomes real. That is the rough argument. If you want to think in terms of off-shell and on-shell, the off-shell particle will become an on-shell real particle if the electric field acting on that in a small enough time scale, because if you are talking about a particle of energy mc square, there is an uncertainty time scale delta t which is h cross over mc square. So in a time scale h cross over mc square, you have to transfer sufficient amount of energy to the virtual antiparticle pair, particle-antiparticle pair, so as to make it real. So the energy transfer in that time scale has to be greater than 2 mc square. So that is one criteria. Usually it works. In this particular case, you will find that it actually matches when we finally find the pair production.